So today we're looking at Newton's third law, otherwise known as action-reaction. More specifically, the third law states that all forces come in pairs. So it says for every action, there is an equal and opposite reaction. What that means is if you have some object A push on object B, then object B pushes back on object A with the same force, but opposite direction. So we can write this as an equation, if you like, where we say the force that object 1 puts on 2 is equal but opposite, so negative, to the force that object 2 puts on 1. Alright, that's easy to say, but what does that really mean? Let's go over some examples. So I have a couple examples here. If you've ever done volleyball in gym class, it hurts. Why does it hurt? Because it's not just you putting a force on the ball is putting a force back on you. Okay? Another example would be if you're skating and you push off the boards. If you're pushing off the boards, the reason you move back is because the boards pushed back on you. Same thing if you are, can't see this, hold on. There we go. If you're on a skateboard, in order to go forward, you push backwards on the ground. And therefore the ground pushes forward on you and you accelerate forward. This is no different than gravity as well. The Earth puts a gravitational force on, let's say, this apple, pulling it down. The apple also puts a gravitational force equal to that on the Earth, pulling it up. This is where people get confused. How can the apple put an equal gravitational force on the Earth? Okay, so force and motion, we need to separate those ideas. So let's look at another example which confuses people. Let's take a large truck. We take a large 18-wheeler, or let's exaggerate, 100-wheeler truck. I know one doesn't exist. It could be a train, maybe. Right? And then we are going to place a bug. That's actually a pretty big bug in comparison to the size of the truck. This is not the scale, so don't be afraid of gigantic bugs. Alright, now the truck's coming along, hits the bug. Now it's going to sound weird, but if the truck puts a force, let's call this F1, on the bug by smashing into it, the bug also puts the exact same force, I'll call it negative F1, on the truck. So why then does the bug get smushed and the truck doesn't? And that has to do with mass. Okay, I'm going to remind you of Newton's second law. So Newton's second law says that the net force acting on something equals its mass times its acceleration. Alright, so in this case, if we're looking at the bug, okay, and this is the only force acting on the bug, then we can say F1 is the net force. Alright, so we have a net force of F1. Now, that equals the mass of the bug. Now, that's going to be really, really tiny. And therefore, the acceleration is going to be pretty big. So, very tiny mass and a large acceleration. However, if you go to the truck, which has the exact same net force acting on it, but because the mass is so big, in order for these two variables to multiply and give you the same force, the acceleration must be incredibly small. It's the same with the example of the Earth. Yes, the apple does put the same force back on the Earth, but the Earth's acceleration towards the apple is going to be immeasurable because the mass of the Earth is so incredibly huge. And therefore, our little bug here is going to undergo a huge acceleration, and that is what's going to cause damage and, well, be the bug's demise. But the truck, obviously, the bug's not going to smash through any windshield or do any damage to the truck. Unless, of course, we do have gigantic bugs like this one that I drew here. So let's try another example. Let's say we have a boat. Oh, that's my laser. I need the pen there. Here's our boat. Okay, and on the boat we have a sail. Here's our boat. Alright. Now, if we have some wind, the wind is going to hit the sail and cause the boat to move. We're going to ignore like fluid motion and stuff that I'll teach you in grade 12. But let's just say it hits the sail and the boat moves. Very simple. Okay. Now let's say we're out sailing and there is no wind at all. None at all. But luckily, I brought a battery-powered fan. And I attach the fan to the end of the boat and I turn it on so that it blows wind at the sail. Here's my question I want you to think about. Will the boat move? So in this example we have a fan cart. So it's just a cart with a fan. Now if I turn it on, the fan's going to push wind in this direction and do the Newton's third law. There'll be an equal and opposite force on the fan, and since the fan is attached to the cart, therefore on the cart in this direction. So if you turn it on, it goes in the direction of our blue crayon there. Alright, now what I'm going to do is take the sail. I'm going to attach the sail right there. We're going to make a prediction to see whether or not this fan cart will move, and if so, will it move in the direction of the yellow crayon or in the direction of the blue crayon. Alright, now I'm recording. Here's our test. Alright, so it doesn't move. Can anyone guess why? Alright, so if we're looking at the sailboat, right, same idea as the fan cart. Let's look at the fan. So the fan first puts a force on the air. And therefore, the air puts a force back on the fan, equal and opposite. Okay? The red arrows are going to indicate the forces that are on our boat. Then, that same air that was pushed out by the fan is going to hit the sail and put a force in this direction on the sail, equal to that it just received. And then, of course, the sail will then put a force back on the wind, causing the wind to come to all but a stop. Therefore, if you look at just the forces acting on the boat, we get sort of an equal opposite pair. This is almost, you can consider them at this point internal forces. Right? It would be like trying to take my hands, I'm on a chair with wheels, and push myself and wondering why I'm not moving. If someone else came and pushed me, my chair would move back that way. So why can't I push myself back? Someone else pushing me is an external source. But me trying to push myself is an internal source and has an action-reaction pair. So I'm trying to push myself back, but I'm also pushing myself forward with the exact same magnitude. So I don't move. And that's the same case as this example here. So now I'm going to give you another example before we go on to some problems, just to see if we got this. Here's the example. And I'm going to show you how terrible I am at drawing now. Here we have a carriage. An old style, wonderful carriage. And it is attached to a horse. See, that's the best I can do. Now, if the horse pulls on the carriage, and due to Newton's third law, the carriage pulls back on the horse with the exact same force, how do they ever move? All right, so lots of good ideas. Let me recap. So how this is going to work, and this is very, very important. Whenever you have action and reaction forces, a very, very important detail is that the action and reaction force always act on different objects. So let's look at just the carriage. The horse is pulling on the carriage, so we're going to have a force in this direction. Let me just call that F, or F applied if you like. Now what about the horse? If we were to draw a free body diagram for the horse is being pulled back. The length should be the same, but I'm just running out of room. Actually, why don't I just change the color? The horse is being pulled back with the same amount of force. But that's not the only forces acting. If they were to try and pull each other on a frictionless surface like ice, and they were all wearing skates or something, then they would just move towards each other until they met, like a tug of war on ice. However, they're not on ice, and that horse will dig its hooves into the ground, and friction will play a role there. And as there's another action-reaction pair there, as the horse pushes back hard on the earth will push forward. And that's a frictional force. We'll talk more about frictional forces in our next lesson, but it'll push forward on the horse with a frictional force. Now there's also going to be a frictional force trying to prevent that cart from moving forward. Oh, the cart is red. Prevent the cart from moving forward. So, in order for everything to move, the horse needs to be able to put enough power into his legs that that frictional force is going to be greater than the frictional force pulling back on the cart. Now, in order to reduce that frictional force on the cart, we give it wheels. All right, I think the force would have a hard time if those wheels were square. All right. So we're going to work on our first sample problem. Now this says we have three boxes, A, B, and C, each with these respective masses. And they're positioned next to each other so that they actually touch. And then we have an applied force put onto box A and causes all of them to accelerate together at 1.5 meters per second squared to the right. We need to calculate the force exerted by box C on to box B. Okay, that last sentence sounds kind of confusing. Why don't we look at each box and draw a separate free body diagram to see what kind of forces are actually acting on them. So I'm going to start with box A. So here's box A. Box A is the one that's being pushed. So it's got some applied force acting on it to the right. Now it's also going to push box B, but we only write the forces that act on that free body diagram, not the forces that it exerts on other objects. But due to Newton's third law, box B will push back on box A, like so. And I'm assuming that force is going to be less than the applied force since they are all accelerating to the right. It wouldn't make sense that it's greater anyways. Okay? Last time, I don't see when someone tries to push something to the right, that object start moving left. That's kind of weird. Okay, so those are the forces acting on A. Let's do B. Box B, now we did have that force that A pushes on B, so the force from A. And B is going to push on C, and therefore, Newton's third law, C will push back on B. So So that's the force we're looking for. Calculate the force exerted by C on B. That's the one the problem is asking for us to solve. But we're not finished, so let's look at box C as well, just so we understand everything in the problem here. So in box C, we only have one force. We're ignoring friction. We're getting to that tomorrow. And that force is going to be the force that B puts on C. Okay. So how do we actually solve for this then? Well, we can apply Newton's second law, F equals ma, to either box A or box B or box C. But an important thing to note is if we were to do it for box B, we would have trouble figuring out what FC is because I don't know what FA is. But then there's something to note here. If all forces come in pairs, what's the pair that comes with FC? And that's this one right here. The force that B puts on C is equal and opposite to the force C puts on B. So these two forces that I've circled have equal magnitudes, just opposite directions. So if I want to solve for this force, I can indirectly solve for it by solving for this one. And that's a problem that's a lot easier. So if I do Newton's second law, I'm going to do Newton's second law for the free body diagram C, where I'm going to write all the forces, the net force, acting on C, is going to equal mass times acceleration. That's Newton's second law. Okay, what are all the forces acting on C? There's only one. Okay, FB. And that's going to equal mass, and I should specify this as mass for block C, because that's the block we're actually applying Newton's second law to, equals mc times A. And I know what those are. The mass is 5 kilograms, and the acceleration is 1.5 meters per second squared. So that gives us a force of 7.5 newtons. Now this force is to the right. The force I'm looking for, which is over here, FC. If you want, you can write FC on B. Okay, is going to be the same magnitude, but opposite direction, so to the left. All right, the next question says we have blocks X and Y attached to each other by a light rope and can slide along a horizontal frictionless surface. Block X has a mass of 10 kilograms and block Y a mass of 5 kilograms. We have an applied force of 30 newtons to the right on block X. So let's draw this. Here we have block X, which has some applied force, like this, which we know is 36 newtons. And we have block Y over here, and they're attached to each other with some rope, like that. And we know the mass of each block X is 10 kilograms, and block Y is 5 kilograms. Draw a system diagram. So that's what I did. A system diagram is just a diagram showing everything that we care about in this problem. Then it says, what's the acceleration of the blocks? Going up to the previous problem, they told us the acceleration, but the important thing to note is all the blocks accelerated together with the same value. And it would be the same here. If two things are moving together, they're accelerating together. It's no different than if you were sitting in a car and I said if the car is accelerating at 5 meters per second squared and you're in the driver's seat, how fast is or how much is your acceleration? Well, it would be the same, 5 meters per second squared. Okay? You're attached to the car with a seat and a seat belt. these blocks are attached to each other with a rope. No different, they're moving together. So what we can do is we can sort of imagine one free body diagram, just like the car, right? Instead of drawing a free body diagram for the person and the car, just imagine that they're together because they're moving together. And the only force acting on them, or the only external force acting on it, there would be tension forces, of course, in the rope, right? X would be pulling on Y, and Y would be pulling back on X. But notice that these are equal and opposite internal forces in this case. So if we're just considering that whole, well, with the car analogy, the car and the person together, then we have a car and a person, or two blocks, with a total mass of 15 kilograms with an applied force of 36 newtons. So we can use that to figure out the acceleration. So F net equals mass times acceleration, where F net, in this case, it's frictionless, and so the only horizontal force acting on it is our applied force. So our F net is our applied force, equals mass times acceleration, and we want to rearrange that to solve for acceleration. So that is going to equal applied force divided by mass, which is 36 newtons, over the total mass, which is 15 kilograms, giving us an acceleration of 2.4 meters per second squared to the right. Now part B says, what are those action-reaction forces on the blocks? So if you wanted to figure out what those internal forces are, we can't look at, say, the car as a whole in our car analogy. Or in this analogy, or not analogy, but in this case, we can't look at both blocks together, because that looks at those tension forces as being internal. That'll just add to 0. So we pick one block. Now it doesn't matter which block you pick. However, you can see that block Y has only one force on it. Oh, there's the bell. Alright, I'm going to have to finish this tomorrow then. Alright, so I'm back to finish the problem. If we want to find the action-reaction forces, we only need to find one of them, because the other one has the same magnitude, but opposite direction. Since we only need to find one of them, we only need to look at one of the blocks, either X or Y. It'll work either way, but Y will be the easier one to work with because there's only one force acting on it, the one we want to find. X, you have two forces, not a big deal, just an extra term in your equation. It'll still work. But let's do Y. So the net force for Y is going to equal the mass of Y times the acceleration. Now the net force, the only force acting on it is that tension force that I wrote. So Ft. And that equals the mass of Y, which is 5 kilograms, times the acceleration of Y, which we calculated in part A to be 2.4 meters per second squared. Okay, so when we do that, we will get a tension of